Welcome back. In today's video, we are going to dive into Kirchhoff's rules. These rules are crucial when Ohm's law just isn't enough to figure out the current distribution. Kirchhoff rules were formulated in 1872 by Gustav Kirchhoff. These rules will help us determine how current flows and how voltage is distributed in more complex circuits. First up, we have Kirchhoff's first rule, junction rule. Imagine a point in a circuit where multiple wires meet. Kirchhoff rule tells us that the sum of all currents directed towards the junction in an electrical circuit is equal to the sum of all currents directed away from the junction. So, if current I is flowing through a junction and current I1, I2, and I3 are flowing away from it, we can write I is equal to I1 plus I2 plus I3. On rearranging, the sum of all currents at the junction equals 0. This rule essentially says that there is no accumulation of charge at any point in a circuit when a steady current is flowing. The current flowing in and out of the junction has to balance each other out. In a way, it is an extension of continuity theorem in electrical circuits. Now let's talk about Kirchhoff's second rule, also known as loop rule. This rule is based on the law of conservation of energy. It tells us that the algebraic sum of products of current and resistance in a closed loop of a circuit is equal to algebraic sum of electromotive forces acting in the loop. Kirchhoff's second rule. While using this rule, we start from a point on the loop and go along the loop either clockwise or anti-clockwise, and then we reach the same point again. This makes the closed loop. Now, if there is a resistor R, this is the direction of current, and we are traversing in this direction, then we consider as plus IR. Similarly, consider there is a cell of EMF E. If we are traversing in the direction negative electrode to the positive electrode of the cell, then we consider this as plus E. Next, mathematically, we can write the second Kirchhoff's second rule as summation I R is equal to summation E. Here is the key idea. As you travel around a loop, the total energy supplied by the battery should be equal to total energy used by the resistors. Let us consider this electrical network and apply the Kirchhoff's second rule. Consider the loop A, D, C, B, A. This is the loop. We are traversing in anti-clockwise direction. Consider the resistor R2. The direction of current is opposite to the direction we traverse, so we take it as minus I2 R2. And the direction of current is in the same direction as we traverse for the resistor R1. So it is plus I1 R1. And we are traversing from the negative electrode to the positive electrode for the cell E1. So plus E1. And from positive to negative electrode in the cell E2. So we get minus E2. So we have considered all the four components. Let us now move on to another loop DHGCP. For the resistance R3, it is in same direction. So plus I3 R3. Next along the resistor R2, it's in same direction of current. So I2 R2, and cell E2 is negative to positive, so plus E2. Next, let's consider the mesh AHGBA. AHGBA. This the resistor R3, it's same direction, so I3 R3. Resistor R1, same direction of current, I1 R1, and E1 is from negative to positive electrode, so plus E1. And at the junction D, we can apply the Kirchhoff's junction rule, which is current entering is equal to current leaving the node junction. So D, I1 plus I2 is equal to I3. So whichever components we need to find in this electrical circuit network, say I1, I2 or I3 or R1 or even, these four equations can be used to derive any component. In general form, Kirchhoff's second rule is stated as the algebraic sum of all potential differences along a closed loop in a circuit is zero. Let us see a practical example on application of Kirchhoff's second rule. Consider the network shown in the figure. Current is supplied to the network by two batteries. Calculate the values of currents I1, I2 and I3. The direction of current are as indicated by the arrows. So first we'll apply the Kirchhoff's junction rule to this point C. At C, current entering is equal to current leaving. I1 plus I2 is equal to I3. Next, we'll apply the Kirchhoff's second rule in this direction for the loop, for the mesh A, C, D, B, A. Now, some of the information is missing here. This is 5 ohm, this is 2 ohm, this is 3 ohm. The direction of current and the direction we traverse is same for both the resistors, as if you observe here. This is the direction of current, this is the direction of current I1. Therefore, 2I3 plus 5I1 is equal to, for the cell E1 it is negative 2. First we pass through the negative electrode, then the positive electrode, so it is also plus E1, which is 12. Next we will consider G, C, D, F, G mesh. The direction of is in anti-clockwise, and both the resistors 2 and 3 ohm, the direction of current is in same direction we traverse. So 2I3, 3I2 is equal to 6, since it's in this direction, negative to positive electron. If we solve for this 3 equation, we can find I1, I2 and I3. 3 missing components, 3 equations. Let us substitute the first one in equation 2 for I3. Substitute for I3 in equation 2 and 3. The color. 2 into I1 plus I2 plus 5I1 is equal to 12, which is 2 plus 5, 7I1 plus 2I2 is equal to 12. So if we substitute the first equation in third equation, we get 2 into I1 plus I2 plus 3I2 is equal to 6, which is 2I1 plus 5I2 is equal to 6. This is equation 4 and this is equation 5. We multiply the equation 4 by 5 and subtract the equation 5, which is multiplied with 2. So this can be written as 7 5s are 35 I1 plus 10 I2 is equal to 12 5s are 60, minus 2 2s are 4 I1 plus 10 I2 is equal to 12. We are subtracting, this becomes negative. This is cancelled. 31 I1 is equal to 48. So we get I1 as 1.548 ampere. Let us substitute this I1 in equation 5. So equation 5, we can get I2 is equal to 6 minus 2I1 This will go here divided by 5. Substituting this, 6 minus 3.096 divided by 5. If we simplify this, we get 0.58 ampere. And similarly, I3 is I1 plus I2 from first equation, which is we get 2.128 ampere. So this is I2 and I3 is 128. So we found the values of I1, I2 and I3. To summarize, Kirchhoff's rule allows us to solve complex electrical networks. Junction rule states that the sum of all currents directed towards a junction in an electrical network is equal to sum of all currents directed away from the junction. And the loop rule states that the algebraic sum of products of current and resistance in any closed loop of an electrical network is equal to the algebraic sum of electromotive forces acting in the loop. If you found this video helpful, don't forget to like, share and subscribe for more such videos.